Buongiorno, buongiorno. Mi chiamo Felipe, non parlo italiano, parlo italiano, parlo English, but I'm super happy to be here. My name is Felipe Hoffa. You can find me on Twitter. I work for Google Cloud, for almost 7 years now. I've been to Codemotion like for a couple of times. I don't know who has seen me here before. Excellent. So I still speak about similar topics, and I'm glad you still chose to come to my talk. So that's a good indication. So yeah, I started as a software engineer 7 years ago, and for the last 5 years, I've been a developer advocate. What's a developer advocate? It's a software engineer with a license to speak. So, yes, I go around the world, I speak a lot, I show what I've done, I love big data, and we are going to do some big data analysis today, and we are going to mix it with machine learning. By the way, who knows BigQuery? BigQuery, we have some hands, good. TensorFlow, we have almost the same hands. But I'm going to review both topics, and if the screen works. Okay, let's get this started. So, the use case I want to solve today is not about seagulls, but about pictures. And the question here is how, if you have 1 million pictures, how do you find pictures similar to this seagull? Many people that are working with machine learning might do it like extracting labels, identify that there is a seagull here, and then looking for other pictures that also say seagull. But to find similar pictures, even if they are not of seagulls, maybe they are of birds, might be a little harder. In this case, in this demo, these are all the similar pictures that I found. So yes, some are seagulls, some are not, but to do this, it's a little more complex. To do it with SQL, it's even more interesting. Same if I'm looking for cats, but I'm not looking for cats by searching for cats, just by showing my system a picture. Or if I have a jellyfish, my system can bring me back all of these pictures of maybe other jellyfish, but maybe the moon too. So there is something interesting happening here, and we're going to get there in the next 35 minutes. So we're going to combine machine learning, which will allow us to identify pictures, with BigQuery to be able to do these queries with SQL at a large scale. And with Data Lab, with a Jupyter Notebook, we're connecting both worlds. So many people know here what is BigQuery. Not everyone knows, so let me show you quickly what BigQuery can do. BigQuery can go over huge tables of billions of rows in very few seconds, and the demo I love giving is going through Wikipedia page views. Anyone knows how many page views Wikipedia has in a month? Any number? 1,000? Maybe more? Million? Billions? Billions, yes. So here in BigQuery, I was running this right before starting this. Do we have Wi-Fi? Hopefully we have it. In one table, only for 2017, I have stored Wikipedia page views, and my table looks like this. At this hour in this wiki, basically the language, this title had this number of views. I'm compressing every page number of views per hour, and if you look at this table is, for all of 2017, has 2 terabytes of data in 54 billion rows. That's a lot of rows. And then if you want to get every page view if you want to, you need to add the 54 billion rows to get the total number of page views. But then you can do more interesting things like searching for regular expressions. If you don't need an index, You can do magic things like going over every row and just run a regular expression. For example, I was looking for things that start with co and end with Sean, just between these two dates in English. I can run this query or any word that you want to run. And in this case, the result was catch. Okay, my contributions, comparison. Anyone wants to give me a different word? Just to make sure that I'm not lying. Any random word. Any palabra. I know that one. Football? I like football. So let's look for anything that starts with foo, anything all double O. In English or in Italian? In English. Okay, let's do it in English. So we will look for English page views, run the query, go over our huge table. Here we can see how BigQuery is processing this. We just got this new cool animation of how we are going over 400 outputs. First, it's reading everything in parallel. It's filtering, grouping, doing the sum. It's been 20 seconds. Okay, good. So yes, starting with FO, foo, and all, we have football coloring. And I didn't get football because, sorry, I put an OL here. But I did get the football hooliganism. But yeah, I'm showing you that you can do things really, really fast, and you can ask for whatever you want and go over this huge table in few seconds. So how do we make this possible? How can we scan things so fast? We just have a lot of hard drives, and we are able to go over all of them in parallel. It would take a long time to do the same search in one computer or in 4 computers, but we are able, one, to leverage our distributed storage. BigQuery is reading, you don't have to distribute your data, you just load your data to BigQuery, and everything is read in parallel, and we just happen to have a petabyte network between storage and computers. I gave a talk last year about how I analyze GitHub. I just wanted to give you a little update since I'm giving demos. Looking at the top projects by stars given by Italians. So for example, with a query like this, you can find in GitHub, if you go over all 2017, what are the projects that people in Italy have given more stars to. And the results I got last year that were pretty interesting is that in Italy, the most interesting project was the Riforma Costituzionale. People were starting that project, and I learned that you can send patches to your constitution. But last night, I updated it to 2017, and the results I got, the most interesting results for Italy were MashApeConf, database de comuni italiani con informazione state cap, an esoteric programming language. But I missed that one. But everyone else got it. Telegram, you love telegrams. And I also found pretty interesting that Redis is getting a lot of stars in Italy. And I learned, I have a suspicion. Well, Redis is a pretty popular database everywhere. Why is Redis popular here? Yes, I learned that last night. The creator of Redis is Italian, lives in Catania, and yeah, it shows up with more stars from Italy because probably maybe he's even here. So well, we try to look at the data center as the full computer, and that's how we connect everything. We have Borg that connects everything through. This is our container platform that we've been running for years, and now we are sharing it with everyone as Kubernetes. And Jupyter is our petabyte network that goes really, really fast. And BigQuery then is able to process data massively without you having to do anything of this. So what is BigQuery? A fully managed data warehouse, processes terabytes in seconds, economies the cloud, and if you know SQL, you're ready to use it. Now let's talk about feature vectors. How do we do smart analytics? How do we go past regular expressions? And let me run a demo that my friend Cass wrote for you. I have it here. I'm not a robot. And I want to look for, I have 3 different demos here. Let me start with Stack Overflow questions. Let me search for text, but I want to search for different text. So for example, I have a question that is how do I redirect, I have this question Stack Overflow, and I want to go through the 10 million Stack Overflow questions and find similar questions with a query like this. Again, we are leveraging BigQuery instead of an index. We're doing everything in real time, and the results will be here at any time, or I will jump to the next slide because, well, this is the query we're using, and this is all my results. And yeah, I have a similarity search here. How do I redirect to another page in jQuery? How to redirect from one URL, jQuery redirecting from an HTML page. This is how the similarity score that we got with a SQL query. So yeah, for a question like this, how do we find similar things? First, we will take each post and separate it in arrays of words. And we want to transform these arrays of words into feature vectors. And once we have vectors, we can define and user-defined functions to calculate the similarity between these feature vectors. And then we can use another user-defined function to calculate the distance. So how do we transform a post into a vector? This is TF-IDF. We're basically looking at not only what are the most popular words, but how popular these words are in our full document. So for example, each Stack Overflow post, we can transform it into the most important words, like where and what's the score for each word. How would I do this with BigQuery? I would ask first Stack Overflow, how I compute TF-IDF. And I ask this question, and then I replied it. I just basically go over each Stack Overflow question, for example, for Reddit. Or, well, I'm doing that with Reddit or with Stack Overflow. And once I get every word, I count the importance of each word, how many times it appears in each document, divided by how many times it appears in the full data set. And that gives me the answer, which I store. I'm showing up. Oh, these are the most popular. Yeah, TF-IDF. So for example, for this question, the question 74,000, the most important words are divisible, URL, short, hash, long. And now this for me is a vector. And now that I am able to transform normal text into vectors, a list of words, I can look at the cosine similarity between them, between these vectors. What's the distance? What's the vector that is closest in this word space to the one I'm looking for? And what my friend Cass, who started this research, did, he wrote, instead of doing it on plain SQL, he wrote a JavaScript function. And BigQuery can run JavaScript questions, so this is how you find the distance between two vectors with JavaScript, and everything worked pretty well for him. Now, what I did on my hand is I took the same thing, but I found a way to just run it not with JavaScript, but with a normal query and finding the distance. But so you have alternatives. You can do it with JavaScript with BigQuery, or you can do it with traditional SQL, but this allows you to find similar documents. If you want to find the code to do this, my friend Casa again made it all available. Classifying Manhattan. Yeah. This is how we start with the documents. We extract each document. We are able to get all of the the TF-IDF vectors. And you can find all this code here and then go and search. We'll come back to how to do. And this is pretty interesting, but we didn't need any machine learning advanced stuff here. We're just doing operating with words. But we want to work with more complex features. We want to find pictures similar to my seagull picture. And that's where we start using TensorFlow. I don't know if you have seen this demo before. The goal here is we want to teach a computer to tell us if a point is inside, like to differentiate between the orange and the blue points. How can we tell? How can a computer know understand the pattern of a spiral? Writing that code is not easy, but that's where the deep neural networks have been able to prove pretty useful. So this is a deep neural network that we allow to learn about the pattern. Starting just by 2 dimensions, is the point at the left or the right or the top or the bottom. We can multiply it. It will find different neurons, different shapes, different. This basically combining these 2 inputs in different ways and in different depths. Our neural network is quickly learning how to identify if a point is in the blue zone or in the orange zone, and it's getting smarter by the second. Basically, what we're doing here, what we want to extract, are these weights, what each internal how much each internal neuron, how much weight to give to each neuron, and how to combine it between them. And well, basically, in our network learned that we have the spiral, and we don't need to write code anymore. We can just use the numbers we extracted here. Let me close this one. This is the easiest example. We might want to do something more complex with, for example, identifying points in the map, and I'll get back there soon. Again, in Google Cloud, we have a lot of services to do this. We have TensorFlow, where you can do your own custom models, and machine learning engine that allows you to run all of this in the cloud. And also, we have pre-trained models that with that you don't need to write your own code. You can just use them as APIs. So Cloud Machine Learning Engine. And we want to use BigQuery to do some pre-processing. So for example, the example I had ready to show you here, just to go back to the example, is how do we classify Manhattan? How do we find if points are inside Manhattan or not? Again, how do you train your computer to tell this? In BigQuery, I have stored millions, more than 1 billion taxi trips, and I can use BigQuery to extract that data. So with this query, I'm extracting the latitude and longitude of each point, and I also have these points already annotated, if they are in Manhattan or not. So I can extract all of this data, and instead of using all of this data raw to train my machine learning algorithm, I can use BigQuery, some SQL queries, to extract the features I want. In this case, is it Manhattan or not? And I can compress how much data I will use to train my network later. Then I can move this data to a Python structure, and I can start plotting things. For all the points I had in BigQuery, now I'm plotting it between Manhattan or not, blue or yellow. And I can do the typical machine learning flow, which is I define my training points, I define my testing points, and I can bring that data finally into TensorFlow, where I have my feature columns, and I can define here my simple neural network with with these hidden units, the classifier, and I can train it. First, before training my network, everything is yellow, of course. After a couple cycles, the network can identify things. If it learns how to classify where the points are without me having to write the specific code. And now my machine knows, oh, this for any given point that you give it, if it's in Manhattan or not, just by learning, just by following this process. Prepare your data with BigQuery, extract billions of rows, train it with TensorFlow, run everything, combine everything in your Jupyter Data Lab notebook. And then, once you have these vectors, once you have defined your model, you can bring it back to BigQuery. You can run these searches. So let me go back to the pictures, which again I have the demo here. Let me restart. Query Smart, our demo here. Let's look for pictures. How are we doing on time? You can, in this case, let's search for pictures that are similar to the yellow car. How will BigQuery solve this? Again, we are looking over a huge amount of images, and instead of having a specialized search, we just run a query like this, which will come back in a few seconds. Give it a second. But if you see the query that is running here, we're just running a huge cross-join between vectors. What did we find? What did our network find? A lot of different cars. Not only yellow cars, even red cars, because somehow it knows that the shape of this one is similar to the shape of this one. And what's the magic behind this process? Again, is our ability to extract a vector, convert each of the images into a vector of numbers that might not make a lot of sense to us, but that allow us to search in this dimensional space. So how did we do this? First, we took 1 million images from Wikimedia, and we stored it in our storage. And we applied a convolutional neural network to extract these vectors. And we imported those vectors into BigQuery. And then we can find, just by the closest images, just by looking for the closest network. Basically, we have this deep neural network, and instead of going to the last step, which gives us the label for each image, we go to the last step -1, and that gives us all the numbers that we use in the vector. With TensorFlow, you can write a script like this that basically uses this model that is already trained, but we extract all of the weights of the previous to the last step, and now we have a new vector. Then to run it over 1 million images, that's the other challenge. How do you run? How do you extract all of these vectors from 1 million images? In this case, instead of doing it in my own computer, I just leverage ML engine. I submit my job, and with a basic GPU, this job was done in about 10 hours, which is pretty cool for 1 million images. And now I can find similar images. Each image that I extracted this vector for is just a series of numbers. I can look for the most similar one and run my query. Again, how do I find the similarity between vectors? Either with an UDF or with plain SQL multiplying, and everything comes back. How are we doing on time? 10 minutes, perfect. So in summary, with the query, we can go over petabytes of data. We can use UDFs to calculate similarity between vectors, and then these vectors, we can either use traditional algorithms like TF-IDF that we use to transform documents into vectors. We can use instead our deep neural networks to convert images into vectors or any other type of complex data that you may have. And then we can do smart analytics over terabytes of data. The applications are many. I have another example if we have time to run it. But there is a lot of places that you would benefit just by being able to run these queries over this space. All the sample code is on GitHub. Search for Query Smart. Kaz do notice how to start this in Tokyo. If you want to find me, you can find me on Reddit, on Stack Overflow, on Twitter, and I'll be very happy to do more of this. Thank you.